Welcome to the course on power quality. So, we will discuss today the power quality improvement in diesel generator set based power supply system with the outline that we will like to introduce in power quality improvement in conventional synchronous generator based diesel generator set, power quality improvement in self excited induction generator based DG set, and power quality improvement in pumping net synchronous generator based diesel generator set, and the power quality improvement in synchronous reluctance based DG set like. So, coming to introduction, a diesel generating set is used to furnish backup electric power to the event of commercial power failure. So, it is kept on standby for long periods of time, and most commonly used electrical machines in DG sets is wound field type conventional synchronous generator. This generator requires separate excitation. So, the system requires reasonable maintenance, and there are copper losses in the rotor. So, the efficiency is also low, and power quality improvement of DG set is generalized with these following generator with conventional wound field synchronous generator, then self excited induction generator, pumping net synchronous generator, and synchronous reluctance generator. Well, coming to the wound field synchronous generator, the most commonly used generator for DG set supply system is wound field synchronous generator with automatic voltage regulator. But the main problem with synchronous generator is that the need separate excitation unit with increases maintenance and cost and reliability of the supply. And the advantage of self excited synchronous generator is that it does not draw any reactive power in case of as in generator. It has the problem of hunting, and self excited induction generator has reduced construction, less maintenance, and no separate source of excitation required. So, easy availability and no hunting phenomena, and as self excited induction generator requires separate excitation capacitor bank. The voltage and frequency regulation are main challenge of the self excited induction generator. Coming to pumping net synchronous generator, the construction of PMS is simple and robust, and pumping net generators are brushless type, and pumping net synchronous generator does not require the field winding and DC supply. So, and voltage regulation is the main challenge because the field excitation is constant because of pumping net. However, it has been observed that MSG with capacitor has the voltage compensation function. And now, this synchronous reluctance generator has rigid construction, less maintenance, and no separate source for excitation is required, as its frequency remains fixed if the speed of primer is fixed, and synchronous reluctance generator requires separate excitation capacitor like SEIG. Its size is more as compared to conventional generator of same rating. It requires large excitation current, and voltage regulation is the main challenge of synchronous reluctance generator. The state of art is most of the research work on DG sets have been focused on excitation control and voltage regulation of wound field synchronous generator, and some researchers have used the variable speed pumping for improvement of power quality and enhancement of fuel efficiency of DG set. And earlier an electronics controller is used with central DC bus to increase efficiency of internal combustion engine for feeding the variable load, and the steady state performance of standard pumping generator driven by diesel engine with a fixed capacitor thyristor control reactor scheme has been used and to maintain the load voltage and frequency constant under varying condition. And self excited synchronous generator has been reported in the literature as good alternative to self excited induction due to its increased efficiency, low maintenance, and rigid construction with constant frequency operation. Now, coming to the operation, the unity power factor operation and power quality improvement of wound field synchronous generator based using 3 lag volt, 4 lag, 3 lag and 4 lag voltage source converters, and power quality improvement and voltage control of self excited generator, pumping net synchronous generator using static compensators, and load compensation of synchronous generator, self excited pumping net generator, and synchronous reluctance based DG sets using the battery energy storage system. Well, these are the typical example of diesel generating set, and application of DG sets you can see typically the power generator in typically in the ships, in marine applications, and then military applications. Then you have a silent DG set for bank and insurance, then high performance data centers, then there are many more applications like, and well, it says typically have a sales infrastructure, agricultural, food and pharmaceutical industries, healthcare, hospitals, clinic and retirement homes, water treatment facility, transportation and logistics. These are the some more applications like on construction side. And the classification of DG set also on the basis of connectivity like grid connected DG set or standalone DG set, on the basis of generator use like conventional synchronous generator, wound field synchronous generator, self acting generator, and the classification on the basis of generator used for permanent synchronous generator and synchronous reluctance generator. Doubly fed induction generator also used some application, and on the basis of heat speed they are used in fixed heat speed as well as variable speed, and on the basis of load like a single phase load and 3 phase load, and these are the some of the configuration. So, I can tell you very interesting the major problem like sometime I mean these DG set have to be related if they are used for feeding the non-linear load or like a single phase load like a telecommunication network. So, those DG sets were derated typically even a 25 kVA DG set was used for only 10 kVA load because it was the non-linear load, and when you have a non-linear load then certainly why you have to derate because losses increases in the winding as well as you will find the voltage unbalanced for other connected load, because the synchronous even in conventional synchronous generator you have a reasonable synchronous reactance of the machine. So, that work as a source impedance, and even from AVR you can regulate the voltage, but the major difficulty with such kind of generator is the voltage distortion is still present at the point of common coupling. So, this is the typical case when I mean you have a like a kind of single phase load on 3 phase synchronous generator, then you will be having a load unbalance as well as the voltage are distorted because if it is a non-linear load and voltage unbalance also present there. So, there what it is you can use the typically I mean like your D STATCOM for providing harmonics to the load as well as reactive power to the load, and it also I mean because here you have AVR normally in wound field synchronous generator. So, that regulates the voltage, but you can maintain the power factor unity of the load. So, this load behave as an ideal load to the generator, and then you not to derate the generator. Moreover, I mean you can operate this generator typically I mean even sometimes we will talk a little later about the optimum fuel zone. So, this you can call it the compensator here, improve the ripple filter, improve the voltage profile, and this compensator compensate for the typically the load, provide the load balancing and harmonical mesh and reactive power compensation on the generator, which generator losses are reduced like. Similarly, you can use of course same compensator for even typically with the capacitor bank with the self acting induction generator, which can be used for voltage regulation here, because here it is not only for you are going to use typically for power factor correction, but you have to do of course the load balancing and harmonical emission. Along with that you have to regulate the typically the voltage also here, like I mean the frequency of course can be maintained with the help of governor control of the diesel engine, but the voltage have to control by the this static compensator. Then you have a similarly like this single phase load with the permanent synchronous generator, in similar to like a self acting generator, permanent synchronous generator also have a fixed excitation. So, for that voltage regulation also have to be provided along with the load balancing and harmonic compensation. You have to provide the load balancing also by using this STATCOM on this your permanent synchronous generator. And similarly, that in case of synchronous reluctance generator also I mean like you can have a again like load balancing and harmonic regulation, and then you have to have a voltage regulation like I mean. So, that typically the role of this your can call it of STATCOM. So, STATCOM capability is more utilized in these 3 generator I mean like a typically permanent generator, synchronous reluctance generator and synchronous your self acting generator compared to your conventional synchronous generator. Now, coming to typically in applications, because you might have a 3 phase balanced load, unbalanced load. In such a situation I mean sometime I mean it is recommended that on the DC link you can use the battery. By providing the battery, then you can operate this DG set in a fuel economy zone, and that fuel economy zone for DG set or diesel engine is it had to be operated between 80 to 100% load, and providing the battery provides a adequate advantage that you can provide the power leveling on the DG set. So, if load is lower, then you can charge the battery, and moreover even under extreme condition because battery may be charged. So, you can even have a load more than 100% also, or it can help you in dynamic load I mean like a starting of the motor from where the energy can come directly from the your typically from the battery along with the generator, and generator is not to be loaded more than the rated capacity, but remaining power comes from the battery as well as the reactive power can be given by STATCOM. So, in such sites like where you have a or such installation where you have a dynamic load like maybe a kind of water pumping or other motor loads where you want to use the DG set for that as a emergency supply, the battery really help us for power leveling on the load side as well as on the generator side. So, that can be used in conventional synchronous generator also, but here of course, you have a for voltage regulation for typically only what you have to do. Typically, you have to maintain the like typically here unity power factor as well as the power generated from the. So, if load is let us say less than 80%, you always generate 80% and charge the battery, but if load is between 80 to 100%, you can feed directly to the load and battery remain floating, but if it is a load is more than 100%, then certainly you can have typically taking power from the battery like so similarly the you can have like a in self action induction generator also, here the voltage also to be regulated as well as frequency can be regulated with the help of your this battery energy storage system, because it can store the energy as well as it can give you energy back to the system like also. Then similarly you have a typically the your the battery along with here your conversion with the permanent synchronous generator as well as synchronous reluctance generator. So, battery provides the additional function, you can call it of power leveling on the generator, and so that the efficiency of the DG set, fuel efficiency of the DG set can be maintained to the full extent, and the load on the generator can be or DG set can be maintained between 80 to 100%, and however the load can go even more than 100%, because you can take energy 100% power from the DG set and more you can take from the battery for the short period like so even to meet the peak demand charges or ingress current power requirement of the load like and well then you can have even a 3-phase 4-wire system also. In 3-phase 4-wire system, your generator may not have even the 4 terminal, even if you have a 4 terminal you not to use you can use the neutral terminal, but you can eliminate the neutral current of the generator side. So, and generator current can be made balanced at unity power factor, neutral current is eliminated, and the fourth leg of the compensator or this D-STATCOM or STATCOM can provide the neutral current for the load. In spite it might have a harmonics and load balance. So, you can call it like again the derating can be avoided, and the excessive which neutral current flows into the generator, even if you have a neutral terminal, that can be also avoided like. Similarly, this even the like a self acting generator may not have a neutral, still you can feed the by taking a 4th wire and the point of the start point of the capacitor bank you can use it typically like as a you can call it for typically for neutral current feeding for the load and providing the load balancing, neutral current compensation, voltage regulation, like all those functions you can do by this compensator. Similarly, for the typically of permanent synchronous generator, you can provide the neutral current compensation as well as you can do the even typically your voltage regulation like and load harmonic elimination along with you can do load balancing also. So, similarly, in the synchronous reluctance generator also along with the voltage regulation, you can have a neutral current compensation and your voltage. So, these are the power quality improvement with the help of this STATCOM you can do in all these generating system and utilize the generating system with the minimum losses and with the improved fuel efficiency, like that is the role virtually, and the voltage typically profile is also improved by using such compensator like. So, now coming to the design part of the DG set, we have taken a typical case study that of the 3.7 kilowatt 230 volt 50 hertz 4 pole for the power quality improvement features. So, these are the typically all 4 generator, we call it wound field conventional synchronous generator, then self action generator, then permanent synchronous generator, synchronous reluctance generator, and with their parameters are given here all the specification as well as rating and then the parameters like which are important for that particular type of machine like. So, coming to the diesel engine, a 5 HP 1500 internal combustion engine is used as a prime mover of the DG set, and then to regulate the frequency, you regulate the frequency speed of the DG set with the typically from the feedback to from the speed, and then you have a PID controller, then throttle actuator to the engine, and then you have a typically the multiplier with the torque, and then that is the typically the power. So, that is the way how the DG set is there. Now, coming to the D-STATCOM design, D-STATCOM design is similar to what, because it is a 230 volt system. So, it is similar to like what we consider already in earlier D-STATCOM, with all these are the typical rating, and you can calculate from this relation the value of capacitor. It comes 1793 and you can select around 1650 microfarad, which is a standard value for the inverter, and then you can have a interfacing inductor typically by putting the all the variables value, and you can have this about the calculated value comes around 3.2 millihenry, and we typically round up to 3.5 millihenry. So, coming to the typically selection of DC link capacitor, DC link battery voltage, the battery voltage certainly should be little more than the what you can operate the inverter in field satisfactorily, So, assuming the modulation index 1, the DC-link voltage is of 10376 and normally for 230 volt, and we normally select 420 volt for the typical applications like because that is a kind of standard rating. Like for the nominal battery voltage 420, 35 cell of 12 volt may be selected with the ampere rating desired by the how much is the backup you required from the battery, and then you can find out the typically the excitation capacitor from this typical lesson, and for the 3.7 kilowatt requires typically order of 2.51 kVR, and you can have a and synchronous that is self excitation require 2 point, and synchronous electron generator require 6.3 kVR. So, now coming to power quality improvement in conventional DG synchronous generator based DG set, and this is the typical configuration that we are considering. The typically here the case history with the battery on DC link and the single phase load, which is of course like I give an example like a telecommunication load or many single phase load are there. Normally we use the 3 phase machine, but we derate it. So, here the derating is avoided by providing the typically the load balancing also, as well as typically the power factor correction and the you can call it the power labeling also, like if load is varying. So, similarly you can think about the many configuration, even you can have a 3 phase load, or you can have a typically the configuration with the self supported DC bus, and of course, we have to use the a control for the STATCOM, which we are using for this here the voltage regulation, load balancing and harmonic elimination. So, you can use the other line typically a window algorithm for single phase 2 wire configuration with self supported DC and compositor based for 3 phase 4 wire with the battery energy storage system, and adaptive theory node based filter algorithm for 3 phase 4 wire system. Just for example, these are the algorithms used for power quality improvement. So, starting with the typically the algorithm of order line, what for single phase load, we take typically a load current and the template what we discussed already in detail in case of your DStatCom and for all 3 phases, and then we extract the you can call it the fundamental active component of current from there. Then we take a averaging of it for load balancing, and we pass on through load pass filter. So, this gives us active component of current for all the 3 phases. Then we regulate the DC link voltage for supporting DC bus, and that also we consider the losses arise to come from generator, and this we consider the amplitude virtually of the generator current. Multiplied the template, we get the 3 phase generator current, which are at unity power factor, and we sense the current of the generator and have a current control typically of your this STATCOM, which is providing the compensation for DG satellite. And these are the typical equations that we sense the only, because it is a 3 wire system. So, we sense the 2 line voltage and calculate the 3 phase voltages, and we calculate the amplitude from phase voltage, and then the template for all 3 phases we calculate using these equations. And these are the of course, to estimation of fundamental active power component of the load current from this your other line. Like here it is the only this coefficient is important, and it gives the very fast extraction. So, this typically the constant, if you keep higher side, filtering will not be good, but response will be fast, but if you put lower side, response will be poor. So, you have to make a compromise for the convergence of this factor, and then once you are able to get all the 3 components, you can take average, because load balancing is provided by that. And of course, for DC link voltage controller, with the DC link voltage error, you can put the PI control, that also have to come active power from the supply. This is for the load, this is for you can call it the loss in the converter, interfacing inductor, dielectric capacitors on the DC link line. And then you have a total active component, like amplitude of the your generator current. So, you have a load component and you have a loss component, and multiply the template with the these amplitude. So, you get 3 phase reference current for the typically for the DG set, and you can have a current control like. And these are typically the case study with the kind of like a your load. You have a single phase, typically the you have a line to line load, single phase load, and these are the generator current. You are having almost very light load later, and so, but you can see the generator current are balanced, sinusoidal and unity power factor, and this is of course the DC link voltage. So, compensator is providing all the compensation for this, and thermal voltage also regulated by of course, and frequency is also regulated. So, coming to with the typically on single phase non-linear load, we have a that was linear load, this is non-linear load from line A B BC. A phase you do not have a load, and they are providing the load harmonic elimination also, as well as load balancing also. That is the reason you see the generator currents are balanced, sinusoidal, and unity power factor, and DC link voltage of course, you will find when there is a load unbalancing, you will find second ripple on the second harmonic ripple on the DC link, but frequency and voltage both are regulated like. And these are the harmonic spectrum, the load current have a quite high TAD, but you can see the generator current TAD is quite low, as well as voltage TAD is also quite low, I mean at the point of common coupling. But if you do not put this compensator, certainly I mean you will find these are the directly the your generator current, and this voltage is also quite reasonably distorted because of the synchronous reference of the machine like. I mean. So, this is another control algorithm, normally use the battery energy storage system. So, we composite observer basically for extracting the fundamental. So, this is the load current, and we are extracting here the fundamental component of current, and then we are taking from sample to hold the amplitude of this current for active component of current, like where we require quadrature for zero crossing detect logic here, and we get this for all three phases, and then we have a load balancing by power averaging of that, passing low pass filter and then putting the kind of limiter. So, we are able to get multiplied with the template. So, we get the reference generator current and then feedback generator current, we get the gating signal. And here of course, you have a observe how you are able to have from your typically original signal to your typically fundamental signal from distorted signal like from the observer. These are of course, again the equations for estimating from the sense line voltage the phase voltage, and the amplitude from amplitude of the voltage of PC generator voltage from the phase voltage, and that we are estimating the you can call it the template of the which are in phase with the phase voltage. And then this is the of course, the observer for to get the typically fundamental component from the load current like. So, of course, these are the typically the observer equations, I mean, and they use the gain constant 2 constant like, and the optimum value of this is 42 minus 2 for extraction. So, once you from sample and hold, you are able to get fundamental wave, and by sample and hold you are able to get amplitude of the active component of current for all three phases, and for load balancing you take average of them, and that give you the amplitude per phase current like for the generator. Moreover, we are able to see that for because we are using a battery. So, we are able to use you can call it the if load is between 80 to 100%, we maintain the same load current, but if it is less than 80%, we maintain the generator current only 80% of the rated, and if it goes more than 100% load, then we maintain to the rated. So, that generator is not overloaded. So, once you know the amplitude of the generator current, you have a phase already estimated, I mean template. So, you get the 3 phase reference generator current, and use the feedback current use the current controller for switching of the your STATCOM. And these are typically like we have taken a kind of case study for 2 different cases, I mean like here. So, you can clearly see here the generator current are balanced sinusoidal at unity power factor, where the load is you can call it like a typically load are unbalanced, as well as load is single phase, I mean like, and these compensators are providing the compensation. So, that generator current are balanced also, and you are able to regulate the DC link voltage like. Then another is that I mean the system is subject to loads of 1 kilowatt and photon, and finally unbalanced load. This is non-linear load, like you can see the generator current are balanced sinusoidal unity power factor, where you have a non-linear load, and then you have unbalanced non-linear load, one phase load is removed. These are of course compensator current, and then you have a DC link voltage frequency and terminal voltage. So, all are regulated here of the DC set, and these are harmonic spectrum. When the load current is 24%, you are able to get the generator current TAD only typically of 3.64%, and the voltage TAD is maintained 1.07%. But if you have a like a typically a you do not use such compensator, then voltage TAD also increases. But you will be this will be the kind of generator winding current where you will have a lot of distortion in the voltage like. Now, coming to the performance of synchronous generator with the battery energy storage along with the battery energy storage system for 3 phase 3 wire load. These are the typical condition we have considered. So, in case of battery, I mean we are operating the generator almost like at constant power generation, and the load is I mean like typically here the even unbalanced load is capable of compensating the unbalanced load, and typically you can see when there is unbalanced load, you will have a second harmonic in the your DC link voltage, I mean like, but voltage and frequency is regulated like. And of course, this is the battery current which you have a second harmonics when you have a less load on the generator. So, some battery charging takes place like. But you can have a load even more than 100% also, and this is the typical case. You can see here the linear load is small load, then non-linear load, and then you have a unbalanced non-linear load. So, all are taken care by the compensator, and you will find the generator currents are balanced and sinusoidal and constant like at unity power factor. So, accordingly the battery go on charging and discharging according to the load requirement. So, battery provides the power labeling in this system like, and the TAD of this you can say the load of 24.93%, but the generator current TAD is only 4%, where the voltage TAD will less than 1% like at the point of common coupling. And of course, these are the typical experimental result with the unbalanced load, but the generator current are balanced, and these are the typically the you can call it compensator current. And this is the dynamics you can say here when you really like typically increase the load, it is you increase the load. So, that is the reason generator current also increases, but remain balanced and at unity power factor. So, load typically load balancing as well as harmonic elimination is also taken care in this system like. And this is a typically unbalanced nonlinear load what we look into the simulation, one phase load is not there, but the generator current are balanced and sinusoidal, and the TAD of the typically of your generator current is also maintained less than 5%, 4.9, where the TAD of the load is 25.5% and the voltage TAD is around order of 4, typically of 4.8% like. This is the typical case of linear load for the compensation of you can call it of your power factor of the load is 0.87, but the generator power factor is 0.99. So, the compensator is providing the power factor typically corrections in this case providing the reactive power of the load like, and as well as providing the load balancing like. And here it is you have a nonlinear load, but the generator current are balanced and sinusoidal at unity power factor, and quite highly nonlinear load of with the TAD of 25.5%, where the generator current TAD is 3.6% and voltage TAD is also 4.1%. And this is the typical dynamics where you remove the one phase load, accordingly the generator currents are reduced like, and system is able to still maintain the channel current, balance current, even you remove the load or you add the load in that case, and still your power factor of the generator is 0.99 around unity, where the load power factor is quite low. And these are typical case of your load more than the battery is providing the remaining power, that is the power labeling case like. You can say generator is providing 4.96, however, you require the load of 5.7675 kilowatt like, and similarly you have a load in between, then it remains the generation remains almost equal to the load like battery is floating. And this is the typical case when you have a here the load increase, so accordingly that does not get reflected typically on the generator current like. And similarly you have a dynamic load, the motor is starting, you can see the motor is starting, but you can see the generator either in voltage or current does not see any variation, and the battery currents for short period it comes from the battery to meet the energy requirement. However, the reactive power can come from the voltage source converter working as a compensator. So, you are not able to see any the starting index current of the your motor load on this DG set, you are not able to see any effect on the either generator current or in the generator voltage at the point of common coupling. So, all those features are taken care in that case like. Now, coming to for feeding a 3-phase 4-wire system, we may have a neutral of the generator, but we not to use it, we are using like this typically a start point of the your ripple filter along with the fourth leg for providing the neutral current and load typically compensation like. And this is typically the again algorithm to extract the fundamental for all 3 phases with this your adaptive theory based notch filter like. So, we get the fundamental current, and by using a sample and hold with the quadrature template, we are able to calculate the amplitude of active component of current for A phase, B phase and C phase. Then we take average for load balancing. We have a DC link voltage regulation, certainly DC link voltage have a some ripple like a second harmonic ripple for load unbalancing. So, that is the reason we use low pass filter. Then we use PI control, this provide the loss and this provide the your load. So, total power have to, active power component have to come from the generator, and multiplied the template, then we get the reference generator current, and with the feedback of generator current we give the gating signal for this voltage source converter of the compensator like. And these are the of course, the algorithm that we sense the 2 line voltage, calculate the phase voltage, then from phase voltage we calculate the amplitude of the voltage, and then we get the template form typically for these. And this is the algorithm for estimating the fundamental active component with adaptive notch filter using these expression. So, here it is the load current and it is the all sample load current. So, from this we are able to get from this algorithm the fundamental current, and from sample and hold we are able to get amplitude of the A, B, C phase active component of current, from which we take the average of both for load balancing, and this is corresponding to PI control or DC link voltage with the feedback filtered DC link voltage. So, this represents the loss and then we get the total amplitude of the generator current with the loss component of the compensator, including the losses in the interfacing inductor devices, connectors and the electric loss of DC link capacitor, and then the active power required by the load per phase. And then once we know the amplitude multiplied the phase, we get the 3 phase reference generator current. We take the generator current feedback and have a current controller for switching of the voltage source converter for this inverter like. And for neutral current compensation, what we do? We take the load current as a reference VSC current, so that it cancel out each other and there is no current goes into the source neutral current like. And that is the source neutral current reference is 0, and initially no load and subjected to RL load of lagging power factor, and then subjected to unbalanced load. So, these are the typical results, like we have a no load, then we have a load, full load, then we have a unbalanced load, one phase load is removed. So, you can find here the power, typically you have a load balancing and power factor correction provided by the compensator of the generator current. So, generator current are balanced and in phase with the voltage, and these are of course 3 phase load current, these are the compensator current, these are the neutral current compensation. The neutral current like the compensator is exactly generating the opposite to the you can call it of your load current, and then DC link voltage is also regulated, voltage frequency is also regulated of the generator. And then we go to typically of non-linear load. So, here you can say there is no load, but where we have a 3 single phase non-linear load. So, here we are providing the even the neutral current compensation. So, that generator neutral current is 0 and your compensator fourth lag is providing the compensation of neutral current, as you see in the opposite of these, and these are the 3 typical compensator current. There are 3 load current and one phase load is removed. So, load balancing is also provided by the compensator like, and you can see the TID of the load current is 31.9%, where the TID of your generator current is only 4.2% and it is a 1.8% TID of the terminal voltage PCC voltage of the generator. These are experimental result. You can just see the generator currents are balanced sinusoidal at unity power factor, and neutral current of the generator is 0, where the non-linear load currents are there, and you have a neutral current of 3 times the frequency of, and these are the of course compensator current, you can call it, look like active filter current and neutral current of this, and you can see the TID of voltage is only 1.6%, current TID of generator is 1.9%, where the load TID is quite substantial, about 36.6% like. These are the dynamics when you remove the one phase of the load. So, certainly the power generated slightly reduces, but the generator current remain balanced sinusoidal and unity power factor, even you remove the load, and neutral current compensation is also provided and DC link voltage is also regulated like. Now, coming to performance of your power quality improvement in self-excited induction generator. In base DC set, in self-excited induction generator, if you look into, we can use the D-STATCOM voltage. Here we have to regulate the voltage, also voltage control, because there is no other way, as well as we have to improve the power quality by load balancing, harmonic elimination, and diesel engine runs at typically at constant speed, and the fixed capacitor bank is connected at the terminal of ACIG, and these are typical. You can see we have a capacitor bank, we have a ripple filter, we have a single phase load, and we have this compensator with the DC link. So, what we have to provide here, we are providing typically why capacitor bank is there, this will provide part of reactive power of ACIG, and rating of the D-STATCOM can be reduced it by say fixed compensation. So, variable reactive power which is required under variable load condition for this generator is provided by the D-STATCOM, as well as the load balancing is also provided, because we are connecting single phase load. In many applications we connect the single phase load like, and this is the certainly the algorithm we are using hyperbolic tangent function based least means algorithm for single phase loading. So, we are extracting typically from load current for A phase, B phase, C phase, the weight corresponding to active weight, active component and reactive component, both weight we are estimating from there, and then taking average of this, and then for active component we take for typically the DC link voltage controller, and then the active component that comes from the generator, but reactive power control for voltage regulation and for providing the load that we calculate from here. So, we get both the component, phase component of 3 phase generator current and 3 phase quadrature component, because for voltage regulation you have to feed some reactive power depending upon the nature of the load, and that we add it, we get the total generator current, and we have a typically the feedback current here, and that we use typically here for the your control of voltage source converter getting signals like. So, this is the algorithm that we sense 2 line voltage, and we have a phase voltage. From phase voltage we calculate the terminal amplitude of terminal voltage, and we have a template calculation from that, and this is the, you can call it active component extraction from this algorithm. I mean, these are, we are using very simple algorithm, but they are very fast and very accurate algorithm. I mean, only the one weight is there for this adaptive algorithm, and this is for providing the load balancing to get only the per phase basis of weight, and this is DC link voltage control virtually we are getting for considering the losses of the compensator, and this we get the total amplitude of the generator current multiplied the phase, we get the 3 phase reference current, and we get active component of 3 phase current. For reactive component, we calculate the typically reactive component of the load current also, and then we calculate the from reactive component, we calculate the for voltage regulation the reactive current required for the D STATCOM. Then we get from because load we have to provide locally, only generator, only part of the reactive power flow should flow from the. So, this is D STATCOM have to provide the voltage regulation minus the load reactive power have to be supplied here, that goes to really into the generator side. So, you have a then with the quadrature multiplication you get the quadrature component of current also. So, you add both phase component and quadrature component of generator current, that give you 3 phase reference current, and then you are able to compare with the sense current and give the getting signal for the generator. And considering the first case of your single phase load, I mean why we are considering single phase, because these DG sets of low rating they are used for feeding single phase load in many isolated applications that I told you, like a telecommunication tower or many other such load. So, this is the typical case that we do not have a load on A phase, we have a load on B and C, and here is the increase in load. So, you can see generator current are increased and these are the compensator current, and these of course DC link voltage which have a second ripple harmonic ripple because of load unbalancing, like, and change of the load is also observed here. And now coming to non-linear load. So, you have a single phase non-linear load, you do not have a load on A phase, you have a on B and C single phase non-linear load, and these are the 3 phase. So, what they are doing, they are providing harmonics as well as providing the your typically the reactive power of the load and providing the load balancing also on the generator. So, generator currents are balanced and sinusoidal also, and this is the typically DC link voltage which have a second harmonic because of load unbalancing. And here the TAD of the load is typically of 28%, but the TAD of current generator current is 3.73, and you can call it the TAD voltage only 2.77%. These are the typical experimental results corresponding to. So, you can see the generator currents are balanced and sinusoidal, and voltage is also regulated, as you can see the generator current, but these are the STATCOM current which are also unbalanced to compensate providing compensation. So, this is single phase non-linear load, I mean you can see, but here you have even a harmonic elimination as well as the load balancing, I mean it is provided, and voltage regulation is only 1%, sorry, voltage TAD is 1%, where the current TAD is 4.3%. And these are the typical dynamics, like I mean when you have a reduction of the load, accordingly generator current reduces, but remain balanced and sinusoidal, and with the typically DC link voltage also regulated, like. So, now coming to this typically of your operation with the 3 phase unbalanced non-linear load with the capacitor bank, of course configuration remains the same, but we put the buoyancy also for providing the, you can call it power leveling, even we are able to do dynamic. So, here we use of course the another control algorithm which called instance symmetrical component theory, used for extraction of fundamental component also. So, from the load current we extract again the fundamental, I mean like using this algorithm, and then we take average for active component and reactive component. Then we have a voltage regulation DC link voltage control, and we have a typically the terminal voltage control that give the reactive power, and minus load power that goes to the reactive component for in the generator side. So, using a template we are able to get reference reactive current, we calculate from amplitude, and with the phase template we get the active component, and we add together we get the total generator current. So, taking a feedback current we do the to current controller. So, that give the pendulum current controller. So, this is the algorithm that we sense the 2 line voltage, calculate the 3 phase voltage, we calculate the amplitude of the voltage and template of the voltage, then we get a extraction from algorithm fundamental component of active component current, then DC link voltage regulation using PI controller, then we get the total active component which have to amplitude of active component have to flow into the generator, and we get the in phase component of generator current by multiplying this amplitude by the template. Then we go for reactive component of the load current, and we go to a voltage regulation with the help of D STATCOM, and the difference of these two have to flow. The D STATCOM have to provide the reactive component of the load locally, only the part of reactive power for voltage regulations will go to the generator current. So, this amplitude we multiplied with the help with the quadrature component of template, and we get the total component of the generator current phase component and quadrature component for all 3 phases, and we have a sense generator current and have a current control which regulate the voltage and provide the load balancing harmonic elimination of this typical case like. And this is the typically the flow chart of your symmetrical component theory algorithm. So, this provides the voltage control, this provides the typically your the power, I mean like typically loss component, load component of both, and then we are able to get the total sum of the both the current and then the feedback current, and we are able to get voltage control. So, this is typically the algorithm from we sense, because it is a 3 wire system, we sense the only 2 line voltage, calculate the 3 phase voltage, get the amplitude, then we calculate the reference grid current for all 3 generator current for all 3 phases, and where the for reactive component we define a factor of corresponding beta which represents the reactive power and angle, and we are able to get for voltage regulation another typically output from terminal voltage regulation. And then of course, we see the performance applying this algorithm for different kind of load. So, we have a single phase load on the generator, it provides the load balancing and reactive power also of the load, and then we have a nonlinear load. You can see 3 phase nonlinear load, it provides the harmonic compensation as well as voltage regulation, and here unbalanced load means the load balancing is also there along with the harmonic compensation as well as voltage regulation of this ICIG. So, here we have a TAD of the load typically order of 19%, but the current TAD in generator is only 3.92%, where the voltage TAD is only 2.79%. So, these are the very stringent requirement compared to the grid connected mode, because voltage also can be distorted. Now, we consider the typically the case where the your generator current remain only 80 to 100%, where the load is less it generates 80%, and when load increases between 80 to 100%, it remains the same as the typically the same as the load current, and when you have a load typically the load less, then it go to again 80%. So, you have a unbalanced load and reactive load, the compensation provided the compensator, I mean all these, but voltage and frequency remain regulated. Now, coming to nonlinear load, we have a nonlinear here load typically. So, it provides the harmonic compensation as well as the load balancing because of single phase load here. So, and this nonlinear load also harmonic elimination or compensation. So, you have a TAD of the load current 20%, where the TAD of your typically of your only load generator current is 4%, where voltage TAD is only 1% here. And these are the 3 you can say the typically the generator current, balance, sinusoidal typically here, and these are typically the compensator current and the load current. And when you have an you can say nonlinear load, you have a balance sinusoidal generator current and the compensator providing the harmonic compensation here. So, you can say load current TAD that much 25.3 and voltage TAD typically order of 0.9% and the current TAD around 1.9%. So, these are dynamics results when you can say one phase load is removed, certainly your generator is not affected because it might be already generating the not less than 80% because battery is used. So, load compensation is provided and load balancing is also provided in this case, and you can just see the load may be even more than or less than because battery is used in that case like. So, these are the typical performance under fluctuating load on that, and then you have a typically accordingly when load is increased, the power comes from the battery charging take place in that cases. So, battery play a role, and when you have a dynamic load like a motor is starting, compensator is able to feed this current with the help of battery. You can see the power comes from the battery, like active power comes from the battery and compensator is able to provide the reactive power. So, you can see the your generator voltage and generator currents are not affected, in spite you are able to start the motor load also from this DG set like. So, now coming to the this performance with 3 phase 4 wire system, we are only providing the neutral of the capacitor for providing the fourth leg with the neutral. So, this provide the neutral current, and generator certainly will not have any even if this neutral current also we have to compensate. So, that the the compensator provide the complete current of the non-linear load neutral current like. So, this is the algorithm to extract the fundamental for all 3 phases, active component and reactive component, and this is active component. We have a DC link voltage regulator, so that we get active component of current of the generator multiplied the template. So, we get 3 phase reference current of the active component, and similarly for reactive component we get the load current. We have a AC voltage controller, voltage control on a PCC voltage of the generator, and from this generated reactive power from the STATCOM have to fed to the load locally, and difference only for to generator side multiplied the template, we get the reactive current of the generator, and we add both, and this we get the with the feedback the control of this 3 phases, and 4th phase we consider the you can call it the reference compensator current, the capacitor neutral current we make 0, and we sense that current and make so that the fourth leg generate exactly the same opposite current than the what you require for the load current like. And this is the typical algorithm. We sense the here the line voltage and we calculate the phase voltage, and these are typically the amplitude of the phase voltage and template of phase. And of course, using the algorithm we get the weight corresponding to 3 phase loads and providing the balancing by averaging this. We have a loss component by PI control regulating the DC link voltage, and we get the total active component of current flowing into the generator side multiplied the template. So, we get the 3 phase active component of current. For reactive component, we calculate by this algorithm again reactive component and provide the load balancing by taking average, and then we have a of course PI control on the PCC voltage amplitude, which give the certainly reactive component amplitude to be generated by the D STATCOM, and minus the load component, only that much flows into the generator, multiplied the from this amplitude multiplying the template, we get the quadrature component flowing into the generator winding generator side. So, we add both, we get the reference generator current from active and reactive component like, and put a current controller. And for neutral current compensation, of course, we keep it like a typically here the capacitor neutral current 0 like power, and fourth leg compensate for that. These are typical the data of the system, and then this is dynamic performance. Then you can see 3 phase load is feeding of lagging power factor, then load unbalancing is provided, but the generator current remain balanced and sinusoidal with the power compensation. This is of course non-linear load, so it provides not only the your reactive power, but it also provides the voltage regulation apart from harmonic compensation and load balancing, both are demonstrated here. Neutral current compensation is also provided here, and you can see clearly the load current here 28.8%, where the your here the your generator current source current TAD is 3.8% and the point of common coupling voltage TAD is only 3.2% like. These are experimental results. So, you can say 3 phase generator currents are balanced, however, the load is unbalanced. So, this compensated providing load balancing as well as neutral current elimination, and here you can see the typically the your single phase load neutral current compensation power, the generator current is 0, however, the source current is balanced like, and TAD of voltage is 1.5% only, where the generator current TAD is 3.6% and load TAD is 38.9% like. And this is the dynamic result when load is one phase load is removed. You can say load current generator currents are balanced sinusoidal, and even the load is removed. So, you will not see any experience on the generator side. Compensator is providing the local compensation of this like. So, can we stop here?